So good morning, chemistry second year, English medium, unit is organic compounds containing carbon, hydrogen and oxygen. So topic is the preparation of ethers. Already in the previous class we discussed the preparation of ethers, especially by dehydration of alcohols. Okay, when alcohol subjected to dehydration in presence of concentrated H2SO4 or H3PO4, based on the temperature conditions we can prepare the alkenes and ethers. Okay, then so let's see here is a Williamson synthesis. It is the most important laboratory synthesis for the preparation of ethers. Okay, Williamson synthesis, it is one of the, it is a very important synthesis for ethers. Yes. So in this process is alkyl halides. Alkyl halides are treated with here is a sodium alkoxide. Alkyl halides are treated with a sodium alkoxide, then here is a ethers are formed. So this is the Williamson synthesis. Alkyl halides when treated with sodium alkoxides, then what happens is in this here is a bimolecular nucleophilic substitution reaction takes place. Then as a result of that here is a ethers are formed. So this is the synthesis to prepare here is a symmetrical and unsymmetrical ethers. Okay, symmetrical as well as unsymmetrical ethers, both kind of ethers can be synthesized in this method. Then yes, here is this is the SN2 attack of alkoxide on primary alkyl halide. Yes, here is in order to synthesize the ethers by Williamson synthesis, then is alkyl halides. Alkyl halides have to be taken as here is a primary alkyl halide in order to get better results. In order to get better results, here is alkyl halides are here is primary alkyl halides. Primary alkyl halides must be taken. Primary alkyl halides must be taken to get the here is better results. Then yes, in this process what here is alkoxide attacks. Alkoxide SN2 attack of alkoxide on primary alkyl halide. Then so this is the alkoxide, sodium alkoxide. Then so in this process what suppose if the ether is having the secondary or tertiary alkyl groups present in the ether, then so we can take that species as here is a sodium alkoxide form. But is alkyl halides always here is a primary alkyl halide is preferred to get the best results. Then yes, suppose simple, so if it is symmetrical ether is prepared, that is our target. Simply here is what sodium methoxide or sodium ethoxide is taken, then it is treated with here is what, then next one here is a primary alkyl halide, we get the here is a ether, symmetrical ether. Okay, so symmetrical ethers means what, then yes, here is both ends of ether are similar. Two alkyl groups are similar size. Then is a diethyl ether, dimethyl ether. Okay, yes, these are the symmetrical ethers. Okay, two alkyl or aryl groups are same or similar. Then next one that is called as here is a symmetrical ethers. So in Williamson synthesis we can prepare symmetrical ethers as well as unsymmetrical ethers. Okay, suppose if any unsymmetrical ether is to be prepared by this process, then yes, that species is taken as in the form of sodium alkoxide. Here is we are taking sodium alkoxide. Then so this is the Sodium is a tertiary butoxide. Sodium tertiary butoxide is taken as alkoxide. Then so it is treated with a methyl bromide. Then simply here is what the sodium alkoxide. Sodium alkoxide, this is the nucleophile. It acts as a nucleophile. Then as a nucleophilic substitution takes place here. Nucleophilic. This nucleophile attacks on the alkyl halide. Then as a nucleophilic substitution. Here is a bromide. It's a Br minus. Bromide is here is a removed as a nucleophile. That's why here is a this is the ether. Then next one. Yes, better results are obtained if alkyl halide is primary. Then in case of secondary and tertiary alkyl halides, in case of secondary or tertiary alkyl halides are taken as in this process, what happens is then yes, elimination reaction predominates. Elimination reaction predominates over substitution reaction. As a result of that, here is what here is alkenes are formed. Okay, alkenes are in case of tertiary, secondary and tertiary alkyl halides, elimination competes over substitution. If a tertiary alkyl halide is used, and alkene is the only product and no ether is formed. Okay, then suppose if the instead of primary alkyl halide, if we take the tertiary alkyl halide is taken, then what happens is then simply only here is a alkene is formed. Alkene is formed. There is no formation of ether. Reason is what? There is instead of primary alkyl halide, as a tertiary alkyl halide is taken, then elimination reaction predominates over here is a substitution reaction. Yes, here is a this is the tertiary butyl bromide is taken. This tertiary butyl bromide is treated with then here is a sodium methoxide. Alkoxide is sodium alkoxide is sodium methoxide. Then simply here is a instead of substitution, here is a elimination predominates. That's why here is a butene. Here is what isobutene is formed, or yes, here is a 2-methyl propene is formed. Then yes, let's see. Suppose is a phenolic compounds. The phenol is treated with a sodium hydroxide. Sodium phenoxide is formed. This sodium phenoxide is treated with the alkyl halide. Then again here is what aryl ethers are formed. Okay. Then there is a Williamson synthesis. Is a alkyl halide treated with sodium alkoxide. Then here is a ether is formed. Suppose in order to prepare here is a aromatic ethers. Instead of sodium alkoxide, sodium phenoxide is taken. This sodium phenoxide is treated with alkyl halide. Then we can get the here is aromatic ether. How can we get here is a sodium phenoxide? Simply here is a phenol is treated with a sodium hydroxide. Then sodium phenoxide is formed. Okay, instead of sodium alkoxide, sodium phenoxide we are taking. This is treated with the alkyl halide. Then so we get the aromatic ether. Then how can we get the here is a sodium alkoxide? Then when so alcohol is treated with a sodium metal, then sodium alkoxide is formed. Okay, so this is about is a preparation of aliphatic and aromatic ethers. So Williamson synthesis, it is the best laboratory method to prepare symmetrical as well as unsymmetrical ethers. Okay, so in this process here is a primary alkyl halides are preferred. Then next one, so this is the SN2 reaction. How it is SN2 is then is a sodium alkoxide attacks on the primary alkyl halide. So this is the SN2 reaction. Then so let's see the physical properties of ethers. Then so when you observe the structure of ethers is there is a R bond, O bond, R. that is what? Then the C bond O. Then the C bond O is somewhat polar in nature. Okay, C bond O is polar in nature because there is a electronegativity difference between carbon and oxygen. That's why here is a somewhat polarity. But the polarity, yes, the polarity of C bond O is not sufficiently effect on, here is a boiling points of ethers. Then yes, when is compare with the boiling points of ethers and alcohols, similar molecular weight contained ethers and alcohols, if we compare, then yes, in general the ethers boiling points are lesser than the alcohols boiling points. Reason is what? Then so when you observe the here is ethers molecules, then here is they cannot form the ether molecules, they cannot form the intermolecular hydrogen bonding. Okay, they cannot form intermolecular, though they are has a carbon CO bond, though it is polarity, though it is having polar nature, but they cannot form the intermolecular hydrogen bonding among the ether molecules. So due to this reason, yes, their boiling points are very lesser than the alcohols. So when you observe the alcohols, there is a alcohols can form the intermolecular hydrogen bonding among the alcohol molecules. That's why the similar molecular weight contained ethers and alcohols, when we compare, then the ethers are having lesser boiling points, very less boiling points than alcohols boiling points. Then yes, this is the due to lack of intermolecular hydrogen bonding. Then let's see the solubility. Here is in general low molecular weight is ethers. Low molecular weight ethers are soluble in water. The reason is what? Then here is ethers can form the hydrogen bonds with water molecules. Okay, so dimethyl ether is when we take a smaller portion to the excess amount of water. By shaking, what happens is ether is completely soluble in water. The reason is it can form the ether molecule, can form the hydrogen bonds with here is a water molecules. This is the intermolecular hydrogen bonding. Okay, then partial attraction force between high electronegative atom of ether and the hydrogen, which is attached with the oxygen in the water molecule. Okay, because of the formation of intermolecular hydrogen bonding with water molecules, low molecular weight ethers can be soluble in water. So when the molecular weight of ethers are increased, then the solubility can be decreased because of hydrophobic character of alkyl or aryl group. Hydrophobic character of alkyl group is increased, then high molecular weight ethers are not soluble in water. Low molecular weight ethers are soluble in water because of the formation of hydrogen bonding.